So it's quite exciting to be here giving this talk in front of my recent past colleagues at Harvard, my current and future colleagues at Northwestern, but also in front of Monica Colpi. Monica was my professor during undergrads in Milan 10 years ago. She taught me high energy astrophysics, and I guess I have to show you that I learned something. So yeah, so I'm going to tell you the latest about what is going on in the X-rays and radio for GW170817. And I'm going to tell you a story of jets that try to make their way through the ejecta. And I'm going to start by establishing a little bit of terminology. So we have a jet in all the models that we'll speak about, and the difference is if the jet is able to make it through it or not. So when I say a jet model, I mean a model where a jet survives these interactions. So we do have surviving ultra-relativistic ejecta after the interaction. And here I stole this plot from Muncie's paper. When instead I'm going to say a cocoon, what I mean is instead that we do have a jet that created that cocoon to start with, but the jet might not have survived. I want to make it clear, though, that the cocoon is something that is also there when we have a surviving jet. But the distinguishing feature of jetting models is a jet. The distinguishing feature of pure cocoon models is the cocoon. So that's just so that we are in the same place. All right, so here is the basic picture. So Brian already told us everything about the kilonova. And we know that is an isotropic component, and that dominated in the UV, optical, and near infrared. Instead, and this is a compilation of all the data and from 70+ teams that worked to put this together. So the way it's convenient to think about is that at early times, the UV, optical, and near infrared was totally dominated by the thermal process. So early times means 15 days. And instead, the X-rays and radio have been always dominated by non-thermal processes from the beginning. So what produces these X-rays? So what are the possible sources that we have to look at here? So there are two main sources that produce X-ray radiation. And the first is the interaction of whatever ejecta is interacting with the environment. And this ejecta can be not strongly collimated or can be collimated. But I want to make sure that we understand that the radiative process is the same, is synchrotron. It's just particle acceleration is the same thing. And the geometry of the ejecta, the properties of the ejecta might be different, but the radiative process is not. Another possible source of high energy emission is the central engine, so a black hole, accreting, or a magnetar. If that magnetar survived, maybe not. So we have these two sources of high energy and radio emission. So you do understand that by tracking this emission, we can learn about the merger, about this kind of outflows, or which kind of outflow is going where, and the environment as well, because the radiation is coming from the interaction with the environment itself. And always we have to keep in mind that there are geometry issues. So we are observers and we are looking at this object from a particular perspective. So that needs to be in the back of our minds always. So let me just start from central engine. And then, so I'm going to discuss central engine emission, and then I'll move into the ejecta interaction properties. So if you do numbers, so the central engine might have produced radiation from inside the kilonova, so the kilonova that Brian just discussed. So the emission from the central engine had to fight its way through this kind of ejecta, and if you do numbers, it turns out that at early times, emission is unlikely to be able to escape. It might have been there, but it was unlikely to escape. So at very early times, I would say that it's extremely unlikely that we would have been able to see emission from the central engine by itself. So what about the other source of radiation at early times, the interaction of the ejecta with the environment? Well, in this case, the key word is literally deceleration. So it's a problem that gives us a natural time scale, which is the time scale over which the ejecta is transferring energy to the medium. So automatically you have two properties that come in, which is the kinetic energy of the outflow that is traveling, and so the mass that you ejected during the neutron star merger, and the environment density. So by tracking this kind of emission, you can learn about these two ingredients. And again, I want to emphasize this is synchrotron emission across the spectrum that we will be looking at, just like Wenfei told us during the afterglow. So let's see. So if we use as the first component of ejecta that we have is the one coming from the merger ejecta. If you use the numbers, and I did not put the numbers conveniently, but if you use the numbers of that comes out from the modeling, yeah, here we go here, from the modeling of the optical light from the kilonova, and I asked the question, okay, which kind of emission should I expect from this matter interacting with the environment? Well, you will find out that this is kind of heavy, so it takes a long time to decelerate, a long time for the radiation to peak, and this is what you would expect. We would expect some radiation in the radio, but at a time scale which is 10 years. So not now. Not now, definitely not now. So if we go instead into the regime of collimated ejecta, also in this case, the key word is deceleration again, because it's deceleration that is causing the beaming of the emitting radiation to open up and then reach me as an observer. So when we started, this is the picture we had in mind when we were sitting there in August waiting for LIGO triggers. And as we heard many times, we had the LIGO trigger and the gamma ray signal. And we realized right away that this signal was very weak. And since this signal was very weak, not luminous, we had two possibilities in mind, which is a low energy fireball on axis, or something that is totally off axis. In both cases, I want you to realize that in both cases, you do not expect bright emission in the radio and X-rays at early times. I think there was a little bit of confusion because I heard that not detecting anything at the beginning was a surprise. I don't think so. This is exactly what we were expecting. And so at early times, you do not expect bright emission in the X-rays and radio, given especially the very low gamma rays luminosity we saw. So here is what we saw at 2.4 days with Chandra. If you're wondering where is there, two beautiful background photons. So it's a non-detection. It's a very important, extremely important non-detection in the X-rays. And the same thing happened in the radio. We got on target together with other teams at 0.6 days after trigger, and we got excited at the beginning, but nope, it's a host galaxy what you're looking at. So the story that you already know is that for the first 10 days, we had no detection in the X-rays and in the radio, but X-rays and radio were detected around the same times, and it's an effort from multiple teams. I want to emphasize that. So here is how it looks like right now. And now it's 260 days after the merger, and this is what we had, and this is our latest epoch before now. And I know that you're dying to know what is going on right now, and this is what is happening. So we had a decrease in the X-rays, and optical is also consistent with that, and radio. And this is a result that you can find in a paper that appeared conveniently last night by Kate Alexander, and you're finding there data that have been released 24 hours ago. So very fresh news. All right, so what is a key message here? We have, for the first time, we can say there is decreasing emission across the spectrum. So now we know we are going down. So we reached the peak and we're going down. So let's have a deeper look of what happened in the X-rays. I'm going to tell you the picture all the way to the peak, and then I'm going to show you our predictions when we were before the peak and around the peak, and let's see what the new observations acquired 24 hours ago are telling us about this particular event. So what you're looking at here is an SCD plot, so spectrum from radio all the way to the X-rays. And I'm going to play the game of showing you the evolution of the STD with time from 9 days all the way to 60 days, which is right now. So what you can see here right away is that radio and X-rays, they are on the same power law, and what you're looking at here is the kilonova. So we have at 9 days a non-thermal plus thermal spectrum. We wait a little bit, and if we go 15 days, so what we find is the very same power law, and we have a thermal kilonova still there, but you can see that the thermal now is getting closer to the non-thermal. So the thermal part is going away, is fading away. And again, very same power law. So you wait, and then the source went behind the sun. I got many questions. Why, Rafi, you did not observe between 15 and 100 days? Because the source was behind the sun for everybody but radio. So we were doing our homework. So what you see at 100 days is a beautiful power law, X-rays, radio, and HST gave us this detection. So the optical at 100 days is also non-thermal. So we are fully consistent with a beautiful, simple power law in the sky. So we play this game all the way to right now, and what we find is always the very same simple power law spectrum extending 9 orders of magnitude all the way from radio to the X-rays. So there are a few points that I would like to take home from this plot, is that it's the same spectrum. We can measure the power law index down to the 3rd digit, is still the same. So it's a very simple spectrum. It's the simplest spectrum you can think about. It's a power law. Which tells you that whatever is powering the non-thermal part might be one dominant mechanism. There is no reason to think about multiple mechanisms that would conspire to give always the same spectrum. And the other important thing is that we are dealing with a synchrotron spectrum. We don't see any break, but we do expect to have a break at some point. The electrons are cooling, so the cooling frequency should be there, and this cooling frequency is always above the X-rays, which implies right away that implies a constraint on the kinetic energy and the density of the environment and kinetic energy of the blast wave that I will go into in the next 10 minutes or so. So first, I want to derive some properties that are independent from whatever is your very favorite model, so jet, no jet. And then we'll see if we can say something about jet, no jet thing. So first of all, we have this beautiful, simple power law spectrum. It's so beautiful and simple that we can use the index to learn, use the theory of particle acceleration to turn the index that I'm measuring from radiation to the index of the electrons that are producing this radiation and to the velocity of the shock that is accelerating these electrons. And if you play this game, you would find out that this kind of slope, which is new to the 0.6, minus 0.6, would favor material that has a gamma, a Lorentz factor between 3 and 10. So the main message that you get out of this little exercise is that the radiation is produced by the radiation that the observer sees is produced by mildly relativistic ejecta. So that's the first message. However, I want to emphasize the fact that me as an observer, I see mildly relativistic ejecta emission does not imply that ultra-relativistic ejecta is not there. It just means that what I see as an observer is that. The second point I want to make is that this spectrum is a synchrotron spectrum, so these observations are telling us right away that the emission mechanism that is producing this emission, but is not telling me at this point anything about the intrinsic nature of this ejecta. It's synchrotron. That's what it's telling me. So I told you until 160 days, let's say to 100 days, the emission was increasing with time, which means that from the observer point of view, the amount of energy per unit time is increasing. So let's just concentrate on the pre-peak, and then I'm going to tell you what's going on right now. And as any other thing in life, if you see something increasing, it can be either fake or real. And I'm going to get into that little explanation of what I mean here. So fake or real is related to these two possibilities that we have. So we might have highly relativistic collimatic ejecta that are not pointing at me, or I might have And in that case, GW 7817 would be like a normal short GRB, just different perspective. Or maybe we don't have this jet, that this jet did not survive, the interaction was there but did not survive. And what you're looking at is a more isotropic kind of transient. So what I'm going to do in the next 5 minutes is I'm going to start with the simplest possible models in both categories. I'm going to show you that the simplest models fail in both cases, and then we are going to see how to solve this problem. So if we start with the spherical cow, the one shell, same Lorentz factor, and then you will see that you would predict a very steep rise of your emission, which was totally fine in the first few days, for let's say 20 days after the merger. However, if we check the prediction versus the data, we would find out that no, we're not going up that steep. So this simple, very simple single gamma fireball does not work. So that's it. That's a message. So how do we solve that? Well, one possibility is that we add structure to the outflow. So we don't have a single velocity outflow. We have structure in the outflow. We have different pieces traveling different velocities. So what happens is that material behind me that is heavier will catch up with me and will refresh me, will give me more energy. So we'll add up more energy into the ejecta. And in this case, the profile that was favored by some of these works was a profile that goes like to velocity to the -5, which I find very intriguing because in supernovae, we do see the same thing. So it's kind of interesting. So here is how things improve if you add a structure to your ejecta, so a structure in velocity. And you can see, yep, we can definitely fit the data. And here I put a question mark because the future evolution of the emission from this blast wave really depends on the structure of velocity that you have, and in particular how much mass is sitting behind a given velocity. If I change that, I can decide how much I will keep rising, if I still have material that can give me energy, or if I stop rising. So there are two possibilities to make this happen in reality, and the first was pointed out in the paper by Kunal. So you might have a tail of the merger ejecta that is traveling into the environment that is accelerating particles, and this is the model in the dashed line. Or you can have material from the actual cocoon. And you can see that it's not possible to tell what is what from the data. But I want to draw your attention to the fact that if the tail of the merger ejecta is the ejecta that is interacting with the environment and producing radiation, you need this kind of densities, which are on the high end, we will see, to match the flux that we see, that we observe. All right, so let's now go into the other another class of models where we do have a jet that survived. What is happening here is that I see as an observer an increased amount of energy per unit time, not because the blast wave is getting more energy per unit time, but just because more and more energy is coming into my line of sight as the blast wave is decelerating. So in this case, it's a fake. This energy injection is fake. It's just because I'm on a different angle. And so if we take this class of jet models, the top hat jet models, which means all the energy here and nothing on the sides, here is how they perform. So you can clearly see right away that we have a problem. These kind of models do underpredict the early time emission. And what this thing is telling you is that this kind of structure, the simplest structure you can come up with, is not right, and you might need some little wing that would enter, so at larger angle, that would enter your line of sight at earlier times and would boost up the early time emission. That's the message. So here you can see that we are putting structure in angle. So before we're putting a structure in velocity. And of course, in reality, it's not that we have to choose. Nature most likely is doing both, right? Okay, so here's, if you play with a real simulation of structured jet that makes it through the ejecta, here is how it compares to observations. We are still speaking about observations at pre-peak. And those are simulations from the group of Andrew McFadyen. So you can see that you can definitely match the data with a structured jet. And in this realization of the model, the angle is around 20 degrees. So what we are finding is always angles of that range. So here is a blow-up from a recent paper where you will find all the details about the actual simulations by Xi and the group of McFadyen. And you can see this is a kind of a busy plot, but the takeaway point is that different parts of the jet. So here the emission is divided up depending on which part of the which angle is coming from. They do contribute at different times, and you can see that the emission that is getting into your line of sight at later times is the one that is most offensive with respect to you. So let's have a look at the energy. How much energy do I have to put in the jet? And how does that compare to short GRBs that Wenfei told us about? So if you take the simulation that I just showed you from Andrew, and here is the kinetic energy profile, and you can see that the jet, which is the part of our outflow that is moving ultra-relativistically, has an energy that is not unprecedented among short GRB jets. So it's not something that we've never seen. That's it. That's the message. And here you can also see how the different models, actually the difference between different models comes out very clear, I think, from this plot, because the real difference is where you put energy, at which velocity you put energy. So what were our predictions? So our predictions, based on what we saw at around 100 days, were two. So the first prediction is that if we were correct, the emission should start decaying. Why? Because we don't have infinite freedom in how much energy to put in the jet. And there is a trade-off between the fact that we have to match the time, the time scale, and the flux level. So if this, so our thought was that, well, if this emission keeps rising, well, that's a problem for jet models. We are running out of energy. That was the issue. The other prediction is that we were expecting to see no spectral evolution. So here is the index. You can't really read it, but it's an index between radio and X-rays. Our prediction was no evolution at all. OK, so what do the data told us 1 day ago? So here's a compilation of you can see a radial light curve and X-ray light curve, and you can see that until peak time, all the models and number of models, they don't really predict a different evolution. But here is what happens at later times. So you can see that some of the cocoon models do predict to keep rising. Our jet models, and in general, models with jets would predict a decay. So what are the two things that we saw in the data? So the emission is indeed declining. So right now, we have strong evidence that the emission is going down across the spectrum. The second thing is that, as I showed you before, is always the same power law, so no spectral evolution. So our two key predictions are actually satisfied so the data are satisfied by the data following our predictions. So here is how data look like if I just overplot on our predictions, and you can see that we literally see no spectral evolution at all. So what we can take home from this exercise. So the first thing is that an ultra-relativistic outflow in this event is not ruled out. This is a message that I really want to convey. There's been a little bit of confusion. It's not ruled out. It can definitely be there, and is actually providing a natural explanation of what we are seeing so far. But let's go back and see if we can say something about the models. So I told you that one of the key features of this model where you have the merger ejecta that is producing radiation is that it needs kind of high densities, 10 to minus 2. And that is important because the density speaks to where the cooling break in the synchrotron spectrum should be. And highest frequency, highest density means that the cooling break should come into your line of sight earlier. So here is a plot where I translated into a plot what I just said. So here you have the cooling frequency. Forget about this part for a second. So you have cooling frequency versus time. And you can see that in ejecta tidal tail models, either this or that, the cooling frequency should go through the Chandra passband. And look at the time scale. So right now we are 260, we are here. So in this model, so you would expect to see a break in your data. I also want to emphasize that in structured, collimated, ultra-relativistic outflows, this should not be the case, no spectral evolution, and that this is also true for purely cocoon models. So the main message here, I'm going to skip because I'm a little bit behind, is that we can actually, so we can actually say that this kind of models that predict the spectral evolution are not favored right now, because we did not see that. We did not see any spectral evolution. So here is my conclusion. We can say that the emission in the X-rays and radio is still non-thermal and has the very same spectrum, did not move. It is decaying with time. The ejecta tidal tail models right now are not favored by the data. I also want to make sure that say that both collimated, short GRB-like outflows and pure cocoon models are still in the game, also because of some freedom that is in the models. But I also want to emphasize that this kind of model with a short GRB-like outflow at 20-ish degrees provides a very natural explanation for the data right now. So very last thing before Ido kills me. So I did this last night, and we realized that if we are correct, this thing should be bright for 1,000 days more. And actually, I think that if you were to ask me, so how we will ever understand what is what, I think that at the end is going to be statistics. So if we have something that depends on the line of sight, which would be the short GRB like a model, and something that does not, I think that the only way to tell them apart and go to town is statistics, and I'm done. Thank you.
Questions for Raffaella? Yeah, Ilya.
So I think that the fact that you're still going to be able to see it for 1,000 more days, the decay might actually give you a chance to distinguish the cocoon models from the structured jet models, because in the cocoon you're integrating over a much larger part of the sphere, so the decay slope should be much shallower, right? That's what we argued, for example, in Lyman et al. Earlier this year.
Yeah, at the same time, I also believe that since the structure and velocity of the ejecta, I don't think is really set in stones. You can still play with that and get whatever you want, to be fair. But I agree with you. So after jet break, the jet models do predict a T to the minus P 2 point something decay. So, yeah.
Avi?
So the fact that the light curve starts going down is very encouraging for another reason, which is if there is a black hole, as we expect, and the matter is falling back, the Eddington luminosity would perhaps introduce a plateau to your light curve. And
yeah.
So where is the Eddington luminosity line in terms of flux at that distance?
Yeah, so we did this exercise with Brian, and we put in the fallback equation and is this, where is Brian? Where Brian is, okay. Is this Eddington? I think we put in your fiducial m dot, right?
Yeah, this is from Stefan did a calculation of the fallback rate, so this is a theoretical curve.
Yeah.
Where is Eddington?
So here you are at 810 to the 39 erg per second.
Okay, so
here.
that's Eddington.
Yeah.
Okay,
Yeah.
so we might.
So it reached Eddington and went up.
It starts. Okay, so it's not Eddington.
Yeah, but you
Yeah,
still
but
have to have it accreting at
Right.
Eddington rate a year after the merger, which I think is really going to
It
be
should go
difficult.
down, right? No.
Well, we don't know.
Okay. We'll see.
But this is all non-thermal. I don't know.
No, I'm not talking about the non-thermal. I'm saying at some point there would be a plateau due to the thermal emission around around the black hole of 3 solar masses or so. And we know where that should be. And we know also the kind of temperature we expect from that accretion disk. So that would be a predictable signal that we can look for, a plateau.
But that's below your lowest observation, right?
So
you go down by almost orders of magnitude.
this is this is the limit that we can reach with Chandra. Literally, is a 9 photon sphere.
They can go down to 1% of Eddington. So.
No, I I think it's the other way around. The lowest where they are is sub-n. So it's super elegant for this mass.
Yeah, let's do that. I think there are some details here. I think at early time you have the opacity, so you don't know what's going on with the accretion. But anyway, other questions for Raffaella? Mansi.
So nice talk, Raf. So I completely agree with you that the fate of the jet is still very much an open question. The question I have for you is, again, looking to the future, right? I mean, how do we solve this mystery? I mean, more than one event. And for example, I'd like to know your thoughts on this, right? If you find a GRB that is intermediate in luminosity between GW170817 and the rest of the cosmological population, could that help resolve this mystery or firmly establish the connection or lack thereof one way or the other? Or are there any GRB properties that you can use to settle this?
I think that if we were just to get yet another a second only element in the class, I don't think I would be able to set the debate. I really believe that the answer is gonna come from samples here. Yeah, I don't think, unless, well, if your VLBI observations, if this thing were to reach a much higher flux in the radio, and you have been successful with seeing what the fireball was doing, like resolving the image, that maybe is also another way, to see what is there, maybe, yeah.
Vicky?
Looking forward, in this one, you made the point that already knowing that the gamma ray flux was low, you were not expecting a bright X-ray emission early.
Yeah.
But in general, how important is it to have quick response in the X-rays? How quickly after the gamma ray, after the gravitational wave signal, would you like to have response in the X-rays?
Right away.
Like minutes, hours?
Yeah.
So
actually in the paper by McFadyen and collaborators, they point out a feature which they call the merger flash, I think. And it's a prediction that you should have this sort of flash right away at all wavelengths that is coming from basically the side part of your jet.
Is that collimated?
It's less collimated. It's still is not HISO, but it's way less collimated than the real jet. And I find this prediction, this particular feature, very intriguing. Yeah.
Vicky, so I think what we want is fast response. We also want arc minute localizations from LIGO. That would be really nice. So we can, yeah. Okay, I think we have to move on to the next slide. Let's thank Raffaella again.
Thank you.